Okay, what if we, on this one, I'm trying to remember what we said we had. Let's say we were going to evaluate this at 2 and 5. All right. What did we get? Uh-huh. This is a previous problem we did. We've already integrated it. And when we integrated this one, I think we got, look and see if I can find the right one. 1/10 u to the 5 halves plus 1/6.
U to the 3 halves.
Oh dear. I hit something wrong. Let's solve for that. So 1/2 du can replace dx, but there's a problem. I still have another x. So what we can do here is with our u, we can solve that equation for x and plug that in to our integrand. So we could say u plus 1 over 2 is equal to x. Now I have two things that I can substitute into that integrand. Okay, we know we're going to have a 1/2 out front from here. This could also be written as 1/2 u plus 1, which might be a little bit easier. So if I do that, I can multiply by this 1/2. And I have x, which equals 1/2 u plus 1 times u to the 1/2. Now all I have to do is distribute the u to the 1/2, and I can integrate that problem. So we'd have 1/4 times u to the 3 halves plus u to the 1/2 du. And then,
Wait, I'm sorry, how did you get 1 u to
u times u to the 1/2, 1 plus 1/2. And then just u to the 1/2 times 1. Okay, so if we integrate, we're going to have our 1/4, we can't forget our 1/4, u to the 5 halves times 2/5 plus u to the 3 halves times 2/3 plus c. It doesn't matter whether you include the plus c there or in the parentheses. If you multiply c times 1/4, it's still a constant. So if we simplify, if we distribute our 1/4, we're going to have, this becomes 1/2, 1/10 u to the 5 halves plus 1/6 u to the 3 halves. Did I multiply those right? Plus c. And we're not quite finished. We're not finished until we substitute back in what we said u was. And u was 2x minus 1? Plus c. Okay, now if you were to look this answer up in the back of the book, it probably wouldn't look like this because they factor out what's common and it gets real complicated. I'll let you stop right there because it's just a lot of math work that can cause a lot of error if you make one little bitty mistake. So you can stop right there.
I have a question.
Uh-huh.
Calculus test let us stop here, or do we have to factor?
No, I believe they would let you stop here.
Okay.
The only problem would be if it were on multiple choice, but I don't think, because it's so time-consuming to change it, that they would do that to you. I haven't seen one that they would expect you, but the back of the book sometimes may show it like this, and sometimes it may show it factored out. But you can stop right there. Okay, this is going to look a little bit similar, but it's the same idea. I think our U is going to be the same in this. So what would U be, Michael?
It'd be 2x minus 1.
2x minus 1. So this part of it works kind of the same way. We're just putting it back together a little bit differently. Du is 2dx, so we'd have 1/2 du is dx. But I have that extra x there again. So we're going to have to do the same thing. Probably should have found a different problem, but I could say it's not placed the same way. Okay, did I solve that correctly? All right. So this time I'm going to have 1/2 times 1/2 of u plus 1 over u to the 1/2. Can we solve that? How do we do it, Iris?
You separate it?
Separate it. So if I separate it, what am I going to have?
U over U 1/2
Okay.
plus 1 over U 1/2.
Okay, good. And that simplifies to? U?
1/2
U to the 1/2 plus
U to the negative 1/2.
u to the negative 1/2. Okay, take a second and integrate.
So like multiply the 1/4 or no? Yeah.
Well, what do you get first?
I got 2 or 2/3 times u to 3/2 plus 2u to the 1/2.
Okay. And so now if we multiply, we get?
1/6 u to 3/2 plus 1/2 u to the 1/2.
Okay, so if we have this, are we done?
No, yeah, let's stop putting U.
We just have to substitute back in what we said u was. So 1/6 times 2x minus 1 to the 3/2 plus 1/2 times 2x minus 1 to the 1/2 plus c. For time's sake, we're not going to get a common denominator and factor out the lowest terms. So we have a theorem for definite integrals that says if we let u equal to, or we let g of x equal to u, if this has a continuous derivative on a closed interval, and f is continuous on the range of g, then the integral from a to b of g of x times g prime of x is equal to the integral from g of a to g of b of f of u du. Okay, so that's the theorem. Let's look at a practical application. Basically, what we're doing is substituting into what we said u was. So if we have the integral from 0 to 1 of x times x squared plus 1 cubed dx, and we're going to let u equal x squared plus 1. What's du?
X squared plus 1.
Du. 2x dx, which I don't have the 2, so we're going to have 1/2 du equals x dx. So our integral we're going to have our 1/2 u cubed du. And to make it a little bit easier, we can plug in the bottom limit into what we said u was. If I plug in 0 into x squared plus 1, I get 1. That's my new lower limit. That way I don't have to substitute back in later. And if I plug a 1 in for x squared plus 1, we get 2. So now when we integrate, we're going to have 1/2 times u to the 4th times 1/4. And we're going to, instead of plugging back in x squared plus 1, I can just evaluate it at 2 and at 1. So we've got 1/8 times 2 to the 4th minus 1, or 15. Let's see, did I get that right? Yes, 15/8, looking at the wrong one. 15/8. You see what we did?
What did you plug into? Oh, did you plug into the?
I plugged this into what I said u was, and that becomes my new lower limit.
Okay.
And I plug 1 in to what I said u was, and it becomes my new upper limit. If I don't do this, then at this point, where once we've integrated, we'd have to go back and plug in x squared plus 1 and evaluate it at the original limits. But usually it's going to be much easier to evaluate it at the new limits. In fact, let's see if I can go back. Let's say that we're going to go from 2 to 5 of, let me just do one that's fairly easy. 2x cubed times this, no, 2x squared. If I try to make them up, something always goes screwy, so I'll just find one that's already made up. All right, so what's u?
X cubed plus 1.
X cubed plus 1. And du?
3x squared.
3x squared plus 1 dx. Do I have 3x squared?
Wait, 1 plus
No, it's not plus 1. Thank you. Just checking to see if y'all paid attention. All right. Do I have all of that?
No, you don't.
What do I not have?
3.
So it would become 1/3 du equals x squared dx. And I can move that 2 to the front. So we'd have 2/3 u to the 1/2 du. Now let's get our new limits. What's the new lower limit going to be? 9. And so this is probably not going to come out real nice. Let me change to the limits they used. We're going to go, instead of from 2 to 5, sorry, Justin, we're going from 1 to 2.
Are you recording?
Yes. So I hope I didn't mess it up. It's possible I messed it up, but maybe he'll get the idea. All right, so if we plug in a 1, what's our new lower limit?
2.
And if we plug in a 2?
9.
9. So when we integrate, we get 2/3 times u to the 3/2 times 2/3. Did I do that right? Evaluated at 9 and 2. Because sometimes it's better to go ahead and make your substitutions at the beginning. It's too easy to forget at the end.
What would you plug the number in?
Okay.
Which number?
So 4/3. I'm going to plug 9 into u to the 3/2. What's the square root of 9? And 3 cubed? 27. Minus, if I plug in a 2, we're going to have the square root of 2 cubed, which is Okay, so the square root of 8, which is 2 square roots of 2. So here we're going to get irrational. And 3 will go into 27 9 times. 36 minus 8/3 square roots of 2, if you wanted an exact answer. Hans?
Should it?
Did I? All right, and I probably can't, this should have been 4/9. So 3 times 4 is 12, and 8/9. Couple of theorems, I think William's already discovered these. If we have even and odd functions, it can save you a lot of calculation. Remember that an even function is symmetric to the y-axis. That means f of negative x is the same as f of x. It is symmetrical to the y-axis. Y-axis symmetry. If we have an odd function, in other words, f of negative x equals the opposite of f of x, we have origin symmetry. And so there is a theorem that tells us that if we go from negative a to positive a of an even function, we'll do the even function first. If we go from negative a to positive a of an even function of f of x, you get the same answer as if you did double from 0 to a of f of x dx. Probably a good example of that, if we think about the cosine curve. Say we wanted to integrate from negative pi over 2 to pi over 2 of the cosine. Okay, those areas are the same, aren't they? This area is the same as this area. So instead of integrating and plugging in both pi over 2 and negative pi over 2, it's always easier to plug in a 0. So we can just double that and go from 0 to pi over 2 of the cosine of x. And that would be a much easier calculation. Generally because it's just easier to plug in a 0. Okay, so anytime you have an even function, if you recognize that you have an even function, you can...
It's just when the exponent.
Okay, cosine and secant are even functions for tangent, for trig functions. If all of your exponents are even, you have an even function. All right, let's look at what it says for an odd function. For an odd function, if you go from negative a to a, now that's the qualification. These have to be opposites of each other, of f of x dx. We get 0. Okay. A good illustration, say if we did from negative pi over 2 to pi over 2 for the sine. It's going to look something like this. And what happens to those areas? Here you have a negative area and a positive area that cancel each other out. So, odd functions. All your trig functions except for cosine and secant are odd. If your polynomial has only odd exponents and no constants, only odd exponents and no constants, then you have an odd function. And you can use this shortcut to evaluate.